For coming. Just the usual reminders to refrain from flash photography. And afterward, please plan to join us upstairs for a book signing. After Professor Randall gives her presentation, we'll have a Q&A. She'll run that. I ask that you please raise your hands, and she will either call on you or we'll get you a microphone. But in any case, please wait for the microphone. My name is Andy Cahan, Director of Author Events, and I'm pleased to welcome all of you this evening. This evening we are joined by theoretical physicist and cosmologist Lisa Randall, who continues her journey to explain the nature of reality seen and unseen, imagined, modeled, and conjectured. She'll take us on a magical mystery tour of the past 66 million years and the events and connections that link us with one another and the universe that surrounds us. If that sounds a bit vague, and it is, it's because I don't know what I'm talking about. But here's someone who does. Please welcome Lisa Randall.
Good evening. It's really a pleasure to be here. Was here a few years ago. I really like this place and this audience. I'm also very impressed that you actually managed to find the entrance. Seems really hard, so I know it's a really smart audience. So you should have no trouble with this. So I'm going to be telling you about my latest book, Dark Matter and the Dinosaurs, the Astounding Interconnectedness of the Universe. And as those of you who've read my previous books know, this is a bit of a departure for me. It's entering different areas of science than I ordinarily do, but it is rooted in the kind of research I do. So, I just want to start off by saying a little bit why I wrote this book and what I was after. And so one of the reasons I decided to write a book was when I was working on dark matter, which is actually where my research is. It has all these implications, of course, for the world we live in, including forming the structure of the galaxies and forming structure of galaxy clusters. It plays a big role. And the kind of work I'm going to talk about specifically that connects it to the dinosaurs makes an even more immediate connection to our solar system and even life within the solar system. So it seemed like a very nice opportunity to sort of bring this sort of more abstract kind of research that I do to sort of somewhat more concrete realities, more immediate in our environment. And it was an opportunity for me to both learn and tell the story of sort of, first of all, can I just ask you, the microphone's over here, I just want to make sure, does everyone hear me? Okay, if you don't, just please wave your hand, because I sometimes move around. So it's an opportunity to tell the story, both of the evolution of the universe, namely cosmology, and sort of what kind of questions we ask in cosmology, and what is out there in the universe, like dark matter and dark energy, but then to also bring that to galaxies, in our galaxy, the Milky Way in particular, and within that, stars and the solar system, and stuff that, you know, we didn't really study as much 20 years ago, such as comets and asteroids and things that move within the solar system, not just the now 8 planets that we know about. And also an opportunity to actually think about life on Earth and how that could be connected to our environment, and what might have been brought to the Earth from the solar system or space, and also how life developed, but also something we do know about, which are major mass extinctions. So it was an opportunity to sort of really tell all of this story and how these different elements are related, rather than just, I think a lot of books and a lot of studies just focus on one area. And for me, it was interesting to see how they all interconnect and what is sort of the big story behind it all. And I think the other reason to be thinking about it is there's a lot of attention now to what's happening to the planet today. There's a lot of changes that are being made very rapidly, both to our environment and to life on the planet. And I thought it was really interesting to think about these questions in the context of how both the universe and the solar system and life have developed. So there's sort of billions and millions of years of history that underlie, and all the sort of determined and also accidental things that happened as our universe and our world within it came into being. So that really is the story that I wanted to tell in this book. But I use this sort of research that I do on dark matter and the extinction of the dinosaurs to sort of frame it. And so in this talk, I'll probably concentrate a lot more on that particular research, but deeper in my heart, I think, is sort of this larger story that I get to tell in the process of explaining that. So, of course, the first question I always get asked is, what is dark matter? So it's really funny because, I've talked to a lot of people about dark matter now. And, if you say dark matter at a dinner table, a lot of people will be like, feel justified in saying, I don't understand any of this. It's all very confusing. But the thing is, dark matter is actually really very simple. It's matter. Matter is stuff. Matter is stuff that interacts with gravity like matter. And that means that it collects in galaxies. It collects in galaxy clusters. It gravitationally clumps. It clumps together. So it acts like matter. Why is it called dark matter? Well, it's not made of the same stuff the matter we're familiar with is made up of. It's not made up of atoms. Namely, it's not made up of charged particles. In fact, as far as we know, dark matter doesn't interact with light. It interacts with gravity, but no one has seen any evidence of its interactions with light. So dark matter is actually a terrible name from a physics point of view, because most of you can probably see my jacket, which is dark, and you see it because it absorbs light. And so dark stuff actually is stuff that absorbs light. But dark matter is actually, it's more transparent. It's stuff that light just goes through. In fact, billions of dark matter particles are probably passing through you every second. And you don't know it because all your senses rely on, at some level, on some atomic or electromagnetic interaction. So dark matter is something that an individual particle, assuming it is made up of particles, which most of us think it is, has a negligible effect because the force of gravity, believe it or not, is much, much weaker than the force of electromagnetism. It's only because there's big, massive objects that we experience gravity. So dark matter has had a substantial influence on the universe as a whole, on the development of the universe as a whole. It has a substantial influence on the way stars rotate today and the dynamics of galaxies. But we don't experience an individual dark matter particle directly so far. So I'm going to explain to you that we actually are pretty confident dark matter is there, but at a fundamental level, we don't yet know what it is. So I am a theoretical physicist. We try to figure out questions like, what is it made of? And by that I mean, is it made up of elementary particles? If it is, what are the properties of those particles? Namely, what are their masses? Do they have any interactions aside from gravity? Does it interact with ordinary matter? Does it have interactions with itself? And is it just one type of particle? Or like with our matter, is it made up of more than one type of particle? So, and it's not just theoretical physicists, but experiments and astronomical observations are out there trying to get a better handle on what dark matter is. So it's actually a very exciting research area today because there's a real chance we're going to make some progress, which is one of the reasons I work on it. So this picture probably some of you have seen before. It tells us basically what's out there in the universe in terms of what it is that carries the energy of the universe. It's sometimes called the cosmic pie for obvious reasons. And so you see in this chart that only 5% of the matter is atoms or ordinary matter. About 25% is dark matter, again, this matter that doesn't interact with light, that is not made up of atoms. And about 70% of it is something else entirely called dark energy. So my research is not about dark energy, but just to clarify, because it's another thing that everyone claims they don't understand, dark energy is, first of all, not the same as dark matter, because it's not matter, which is to say, it doesn't clump. Dark energy is uniform. It spreads, and it's probably been there as a constant, and it's spread throughout the universe. What distinguishes it from dark matter is that dark matter is made up of matter. It's made up of particles, probably, whereas dark energy is just energy. It's not made up of matter. It's there even if there was no actual stuff, in the sense of no actual particles, no actual matter. There could still be this dark energy in the universe. It's something Einstein taught us has meaning because all energy can affect gravity. So this dark energy in particular does affect gravity. And the reason we know about the dark energy, or the reason we discovered dark energy, I should say, we know about it for other reasons too, is that it leads to not just an expansion of the universe, but an acceleration of the expansion of the universe. Now, the expansion of the universe, as I'll say in a minute, is a linchpin of the Big Bang Theory. It tells us the universe is expanding. Late 20th century, where people discovered dark energy, they actually were trying to measure the deceleration parameter. They were trying to figure out the rate at which the expansion of the universe was decelerating. And much to their surprise, and a tribute to their scientific, ethics or whatever, or solidity, they actually realized that what their data was supporting an expansion, an acceleration of the expansion, not deceleration. And it's been supported by other detailed measurements, such as detailed measurements of the cosmic microwave background radiation, for reasons I can explain. So this is what the universe is made up of. Now, a lot of people are disturbed by this picture because there's two big chunks that say dark in them. And so they say, this is saying that we don't understand 95% of what's out there in the universe. So the first thing I would say is that I actually think it's kind of amazing we actually understand 5%. I mean, that's kind of an incredible thing that we know what that 5% is when we understand at a really detailed level. I mean, that's the kind of bread and butter of the stuff I do. It's the standard model of particle physics. We understand what it is. However, what those people don't realize is that we actually don't really understand that 5% either, because there actually is a big question of why there's matter left around at all. In other words, if there had been equal amounts of matter in what's known as antimatter is stuff that carries opposite charge and can annihilate, it would have all annihilated by now, and we wouldn't be left with any matter. So it's actually only because there was an asymmetry. There was more matter than antimatter. And how that happened is actually another big outstanding question. So we really don't understand 100%. But we understand quite a lot, having said that. But the other thing that I think is actually very interesting about this chart is that, I don't know about you guys, but I like dessert. And, if I had any one of these pieces of pie, if I had dark energy slice, I'd be pretty full. But even if I had just atoms, it would be like a slice of pie. In other words, you can see all these slices of pie. And in principle, the amount of dark matter could have been 13 trillion times bigger than the amount of energy in atoms. The amount of dark energy could have been negligible or enormous that it was 100%. The fact that we can see all these components is actually a really interesting thing. And it means that even though they're dark, maybe there is some connection, because it might just be a coincidence, or it could be that there's some underlying reason why these are so comparable. And you might not think of them as comparable, but really, if you think about the range of possibilities, they really are very similar. The amount of dark matter is about 5 times the amount of ordinary matter. That is actually remarkably similar, and maybe is the clue as to what it is. And as I was saying earlier, all of this is hinging on the existence of the Big Bang Theory, and also supplemented by something called cosmological inflation. So the whole first section of my book is about cosmology, but I have one slide here. But basically what the Big Bang Theory tells us is, in fact, that the universe is expanding. What it doesn't tell us, despite the name, is actually what banged. It doesn't tell us what was there at the very beginning. It tells us what happens later. And by later, I mean pretty soon afterward. And in fact, very soon after whatever it was that started the universe on its expanding trajectory, there was something called cosmological inflation, where there was really an exponential expansion of the universe. It's kind of interesting, because a lot of the scientific debates, as I learned when writing this book, over the years have been, do things happen slowly, or do they happen sort of quickly, catastrophically? That's true for life, that's true for evolution, it's true for the universe itself. And in fact, both play a role. In the beginning, there's this big, rapid expansion known as cosmological inflation. And afterwards, there's a somewhat slower expansion according to the Big Bang Theory. And we understand that this is right because of detailed measurements that are made. One of them is, in fact, the expansion of the universe, the rate at which galaxies move apart from each other. Another is detailed measurement of the cosmic microwave background radiation. Others have to do with the amount of nuclei in the universe established. So these have really been well studied. And the cosmological inflation has been verified in large part by looking in detail at the cosmic radiation. So this is all pretty solid stuff. Like I said, there's big unanswered questions. How did it all get started? Are we the only universe, et cetera? But within our universe, within the expansion of our universe, a lot has been measured, and we understand quite a bit. So in other words, this is not speculation. We know dark matter exists. Although we don't see it directly, we do observe its gravitational influences. And in fact, the way we first knew about dark matter was because it affects the motion of stars in our galaxy. Actually, even earlier than that, in the 1930s, it was observed that galaxies, and what are known as galaxy clusters, which are gravitationally bound groups of galaxies, move faster than they should. If there had just been the visible matter, they shouldn't have been moving as quickly because they're responding to the gravitational potential established by the matter that's around. But no one really trusted that result, so really the idea of dark matter didn't really take hold until like about the 1970s, when Vera Rubin and Ken Ford did detailed measurements of the velocities of stars in our galaxy, the Milky Way, and they found that those stars are also moving faster than they can be accounted for just by ordinary matter. And so this was really the first pretty solid evidence that dark matter was out there. But I'm going to tell you a couple of other ways we know about dark matter, just because I think they're intriguing in the sense that, in a way, you're looking more directly at where the dark matter is and mapping it out. And one of them is known as gravitational lensing. Even though we literally don't see it, we can see its influence on light. So the way it works with gravitational lensing is there's some bright object, that's that star over there, and it could be behind some dark matter. So there's dark matter in between us, we're looking, we have telescopes, and whatever bright object is there. Now, that bright object can emit light, and that light will be deflected around the dark matter because of general relativity tells us that light will bend in the presence of any source of energy, including dark matter. So even though we don't see the dark matter, we see its influence on light. And the consequence of this is that you would project back and see multiple images of the same object. So gravitational lensing is, in a way, you are kind of seeing dark matter. You're not seeing the light emitted by the dark matter, but you're seeing its influence on other light objects. And probably the most convincing evidence that it really is dark matter and not just some modification of gravity, which for some reason people think is a less drastic assumption than dark matter. I mean, modifying Einstein's equations would be very, very radical. I mean, the existence of dark matter, I don't know if I've convinced you, but it's a pretty simple assumption in a sense. It's just the assumption. I mean, we've known since the time of Copernicus that we're not the center of the universe. So it might also be that the stuff we're made of is not central to the energy density of the universe. That doesn't seem so crazy. And the existence of this matter that doesn't experience light is not such a big assumption. It seems a very natural assumption. I mean, as I said, I think the more amazing thing is that the amount of dark matter is so comparable to the amount of ordinary matter. But nonetheless, people are skeptical, and also you want to know more about the properties of dark matter. So this thing called the bullet cluster and other clusters like it are actually extremely interesting in this regard. So what the bullet cluster really is, it's the merging of at least two different clusters of galaxies. And the reason that's interesting is that clusters of galaxies have both gas in them and dark matter. But gas does interact. So when they try to merge together, the gas will get stuck in the center. And you can observe that happens through X-ray emission. So you see that there's bright gas in the center. But the dark matter doesn't interact either with the gas or with itself to whatever extent we've measured it. And that dark matter just passes through. And through gravitational lensing, you can measure the dark matter on the outside. So this is something that really shows it acts just the way you would expect dark matter to act. It tries to merge together, the visible stuff gets stuck in the middle, and the dark matter goes right through. So, in other words, there's a lot of observational evidence, and this is just a few examples that dark matter really does exist. Where is the dark matter? Well, it's everywhere. As I said, there's dark matter right here, but dark matter is on the whole in an enormous spherical halo around our galaxy. Our galaxy basically consists of the Milky Way plane, which is actually primarily visible matter, surrounded by an enormous spherical halo of dark matter. Now, it's an interesting question why ordinary matter is in a disk, whereas the spherical halo of dark matter is still present. And it's going to be important from my dark matter story with the dinosaurs, so let me just tell you. Ordinary matter can radiate. Ordinary matter interacts with light. And because of that interaction, it can emit light and cool down. So whereas dark matter stays in the spherical halo that it got formed in, ordinary matter can radiate and actually collapse into a disk. And it's a disk because angular momentum is conserved, the speed that it's rotating. So basically, you end up with this structure where you have this Milky Way disk, which has gas and stars in it, which is why if you get outside of the city, you have a chance of seeing this band of milky light across the sky, which is the Milky Way. And so even though there's less ordinary matter, according to the energy count, than dark matter, where we live, which is inside the disk, there's a lot more ordinary matter than dark matter. So I kind of think of dark matter as sort of the unsung hero, because it actually was really important. We ignore it because we don't directly detect it. But if you think about it, the history of physics is a lot of things that we don't see that are actually essential to our existence. And so in some ways, I think, dark matter is like the unseen masses of society. There's more of it, essential to structure, but we ignore it, focusing on the sort of the leaders. But the important thing about dark matter is it actually, and I go into this more in the book, it actually helped establish the blueprint of the universe. Because had dark matter not been around, in the lifetime of our universe, we wouldn't have actually been able to form galaxies in the first place. And there's essentially two reasons for that. One is that early on, there's just radiation in the universe, but radiation redshifts away and matter takes over. And structure can't form from radiation. I mean, you've never seen a light ball. You see a ball of matter. So early in the universe, matter can collapse when matter comes to dominate over radiation. But because there is dark matter, there's 6 times the amount of matter than there would have been otherwise. And that lets this happen sooner, giving more time for structure to form. But the other reason is that dark matter doesn't interact with light, and light would actually wash out the structure. So if you just had ordinary matter, stuff the size of galaxies didn't have a chance of forming in the lifetime of our universe. So dark matter plays an important role in the fact that we actually have galaxies. And if we didn't have galaxies, we wouldn't have our Milky Way, we wouldn't have stars, we wouldn't have anything that we know today. So dark matter really does play an essential role, or has played an essential role. But as I said, there's a lot we still don't know. This is all stuff that we know, but there's still a lot of stuff we don't know. We don't understand at a fundamental level what the nature of dark matter is. We don't understand dark energy in the sense that we don't understand why is there the amount of it that there is. And as far as ordinary matter goes, we don't understand this question of why there's more matter than antimatter. And so these are big questions for cosmology, all of them, and I've thought about them all. But I'm focusing on dark matter, as I said earlier, because I think it's the most likely that we're going to make progress on it. I can't guarantee that it will make progress on it sooner, but I think it's the most likely for progress, in part because of all the new theoretical ideas, but also because these ideas have a chance of being tested, or at least some of them, through both experiments going on Earth and in the sky, and also because of astronomical observations that can tell us more about the distribution of dark matter. So now, having said all of that, I'm going to actually talk about my research and actually connect it to the dinosaurs. But my research, I'm going to tell you right from the beginning, this is speculative. I am not promising this is right. But it's an interesting hypothesis for what can be out there in the universe. And I should say that I am a theoretical physicist, and I call myself a model builder. And one of the reasons it's important to build models is because when all these experiments happen, when all these observations happen, they sort of need to know what they're looking for. It's detailed stuff at this point. It's not just straightforward. So by having models, you have targets. You know exactly what you're looking for. So you can see which of these ideas is right. So I feel completely justified whether or not this is likely to be right because it's something that we will know about. And as I'll explain to you, by measuring the motion of stars in our galaxy, we'll be able to tell whether or not this dark disk that I'm going to describe exists. Okay? So I'm going to talk about a distinctive type of dark matter, not this dark matter that's in the spherical halo, but a distinct type of dark matter that will be distinguished by the fact that it does interact. It interacts in its own way, and it will actually form a disk like our Milky Way disk. And if it does so, it would actually affect the solar system, exert a different gravitational influence, and it could actually trigger comet strikes for a reason I will explain. And one of those could have been the one that killed the dinosaurs 66 million years ago, and also 2/3 of the other life on the planet. Okay. So what did we do in our research? Well, our basic insight is going to sound pretty simple, but it's an important one, and it hadn't been done before. And as I said earlier, why should ordinary matter be special? And why should it be the only one that's special? So if you think about ordinary matter, if you think about the Standard Model, or even the little bit that you probably do know about anyone would know about ordinary matter, we know it consists of all sorts of different types of particles. It consists of quarks, it has electrons or photons. There are many different types of particles, and they carry different charges. Yet when we think about dark matter, we tend to assume that it's just one thing, one non-interacting particle, one very weakly interacting particle. So we made what seems like a pretty harmless assumption of saying, maybe that's not true. Maybe a small fraction of the dark matter is distinguished, and it's distinguished by the fact that it experiences its own interaction. And by that, I was thinking about an interaction very similar to charges interaction with light, except it's its own light. It's not the light that our matter experiences. It's what I call dark light, because it's the light that dark matter experiences. So dark matter particles are charged in a way that our matter isn't. So just like dark matter doesn't experience our light, maybe our matter doesn't experience this light that this small fraction of the dark matter has. And it's important that it's a small fraction because we do know a lot about the bulk of the dark matter. And I have to say, this is the kind of research that, you know, if you'd asked me originally, like, why would you look at this? I'd say it's crazy. We don't know what most of the dark matter is. Why should we worry about this small fraction? But if you think about it, if we had that logic, we would never think about ordinary matter either, because ordinary matter is only a small fraction of the energy. And the reason ordinary matter is so important, aside from our selfish hubristic instinct to study it, is that it has interactions, which is why we have all the interesting structure that we do. So if this fraction of dark matter does have additional interactions, it could be well worth studying. And the other basic insight that really resonates throughout the book and throughout my research is that it really brings in different ideas. And one of the reasons this was fun for us was, although this distinction might not sound so meaningful to you, we are particle physicists, my collaborators and I, we're not astronomers. But the kind of research we did actually ended up telling us something about that the shape of galaxies themselves could be very different than people had thought. And that means that it's something that you can measure through astronomical observations, like the motion of stars. And in particular, what we observed was that if this small fraction of dark matter radiates, and again, it's not radiating ordinary light, but radiating its own type of light, dark light, it too could collapse in a disk, just like ordinary matter did. And furthermore, the other interesting observation we had was that if the dark matter particle is actually heavier than a proton, that disk would be expected to be narrower than the Milky Way disk. So you would end up with a narrow dark matter disk inside the disk of the Milky Way. And the fact that it's narrow is important because it also means it's denser. Just like ordinary matter is denser because it's in a disk than dark matter, even though there's less of it. Even though there would be less of this type of dark matter, if it's sufficiently dense, then it would also be very important. So this is the picture we end up with. We have the dark disk. I don't know if you can see it. Yeah, you can see it. That's sitting within the Milky Way disk. And although it's a small fraction of the dark matter, there's still, after all, that enormous spherical halo. This dark disk could be influential because it can influence the motion of stars. And in particular, it can influence the motion of stars as they go in and out of the galactic plane, which is important because it means that it's not just an abstract notion, it's something we can actually look for. And one of the really wonderful things when we did this research was, and as particle physicists, this doesn't happen very often. I mean, we were thinking about what is the measurement we would like to see done in order to test whether this idea is right. After all, it seemed like a cool idea. I mean, it seemed like something we should know about. It would affect the motion of stars. And it turned out that we were finishing this research in the summer, and that very fall, the European Space Agency was set to launch something called the Gaia Satellite, which is out there now making observations. It's now been in orbit for a couple of years. And what it's doing is it's measuring the position and velocities of about 1 billion stars in the Milky Way. And by doing that, you can then deduce what is the gravitational potential. I mean, it will deduce many things, but one of the things we'll find out is what is the gravitational potential. And in particular, is this disk present? And if it is, what are its properties? So again, this is one of the reasons to do this research, because that way, when they do it, they can actually distinguish what it would look like with a disk from what it would look like without, and thereby really establish whether or not such a thing exists. But, as you can tell from the title of my book, there are possible other consequences of a dark disk, and I will tell you about those now. And I just want to say, like, the whole second section of my book is really not so much about cosmology, but it's really about the solar system. And I learned an enormous amount. And so it's not just about planets, which we all know are in the solar system, but about comets, asteroids, where they're located, the rate at which we know they hit the Earth, how we can tell what's out there, like what is the evidence that there have been impacts on the Earth. And and also about life and extinctions, and of course the extinction of the dinosaurs gets its own chapter. So interesting. But this is what our solar system looks like. There's the 4 rocky inner planets, the 4 gaseous outer planets. But in between, there's the asteroid belt, There's a lot of asteroids. This isn't all of them. And there's also some near-Earth asteroids, ones that are in danger of coming close to the Earth or crossing the Earth's orbit. But the asteroid belt sits in between. And basically, asteroids, they sound exotic, but they're basically just rocks. And they're rocks of all different sizes. They range in size. And actually, extra planetary material hits us all the time. The question that's of interest to us is, when does big stuff hit? A lot of stuff hits and just burns up in the atmosphere. But then we care about when other stuff hits. Now, the other thing that's in this is right outside Neptune is something called the Kuiper belt. And actually outside that is something called the scattered disk. And the scattered disk is important because it is the source of short-period comets. So the stuff out there, remember, is stuff that's frozen. So the stuff there is really frozen, but when it becomes near the sun, it has volatile materials that can then produce the dramatic comet tails that we see. So the thing to notice about all of this is that stuff's really hard to see because all of this stuff is non-reflecting. There's a lot of actually organic matter in there. And organic matter is carbon-based, and carbon-based is really hard to see. It's going to absorb a lot of light. So since the only way we can see the stuff is by reflected light and some infrared light, its stuff is really hard to see. Comets we can see once they emit tails. Asteroids we're looking for. But this is one of the reasons this is hard to look for, and it's one of the reasons we're actually learning about it even now. I mean, we really are getting a lot more information. And those of you who have been following New Horizons know it went to Pluto and sort of out there in that Kuiper belt. But in addition to all that stuff, there's something called the Oort Cloud, which is the source of long-period comets. And short period is less than 200 years, just some arbitrary definition. And long period is greater than 200 years for an orbit. So basically, short-period comets are ones that you have a chance of seeing, in your lifetime, maybe even twice. But long-period ones you're probably never going to see. But the ones that come from the Oort cloud are long-period comets. They're much further away. And they're really thousands of what's known as astronomical units. Astronomical units is basically the distance between the sun and the Earth. So this is thousands of times further away from the sun than the Earth. And that's really important because something that's that far away is that much less weakly gravitationally bound. In fact, it's a square because the gravitational force goes like 1/r squared. It's 1/r distance squared. So it's very weakly bound stuff out there. And the reason that's important to us and our story is that it means that anything that kicks it could potentially knock it out of its orbit. So in particular, if there's some additional gravitational force, for example, from a dark disk, that could potentially knock comets out of their orbit. And then they have a better chance of coming towards the inner solar system where they could hit the Earth. And stuff does hit the Earth, not just this stuff that knocks out of the Oort cloud, but lots of stuff. Asteroids hit more often than comets. They hit going pretty quickly. Comets are going a bit faster. One of the first craters that was found in the United States, I think the first actually found in the United States, is an impact crater. Is known as the meteor crater, also sometimes called the Barringer crater, after Daniel Barringer, who actually was a mining engineer and businessman. And it's actually a pretty fun story. So basically people weren't really convinced that this was an impact. And it is coincidentally very close to where there's a bunch of volcanoes. So it wasn't crazy to think that it could have been a volcanic crater. So you had to find out what would distinguish this kind of crater. And there were things that actually were very misleading at first, such as the fact that it's very round. Because you'd think if something hit from outer space, it would have some directionality in it. It wouldn't be something circular. And I talk about this also in the book, is the reason you have these circular is really what happens is there's an impact and then a shock wave. So it's really the explosion of the shock wave that forms the crater, which is why it ends up being round. So people learned a lot in studying this, and Barringer was very critical in establishing that this really was an impact crater. On the other hand, he wasn't so successful in his business venture because he thought there was going to be a ton of iron because that had fallen from outer space, but not thinking about the fact that most of the stuff was going to burn up in the atmosphere and there wasn't very much that actually hit the Earth. So he was successful in establishing an impact crater, but not so successful in making his money back in this adventure, although he did benefit from other mining adventures. In order to do our research, Matt Reese and I, in terms of the dinosaur study, we were actually looking to see whether big impacts, not just small impacts, but big impacts had any evidence for periodicity. This wasn't an original insight on our part. Other people had observed that there looks like about 30 million year periodicity in the large impact crater record. Actually going and reading the literature, though, however, it wasn't actually clear how solid this research is, or this effect is, it's really borderline. Some people say it's there, some people say it's not, and everyone does it differently. What's your definition of big? Like the last 250 million years, the last 500 million years. So we looked at the last 250 million years for craters bigger than 20 kilometers, which means the thing that hit was probably bigger than a kilometer, which is about the factor of 20. But if you remembered anything else for this talk, you should remember that there's something called the Earth Impact Database on the web, which is just really cool. It's like a list of impact craters people have found over time. So you can find out the age and size of all the impact craters that anyone has ever found on Earth. Now, remember that that list is going to be only a very incomplete record of what's actually hit the Earth, because, first of all, 2/3 of the surface of the Earth is ocean, so you don't stand a chance of seeing the stuff that hits there, and other stuff can erode away. But this is the record we have. This is the record we had that we wanted to see whether it was periodic or not. Now, and we found that it more or less was. Evidence is weak, but with a disk, we were able to really establish what was happening. And what was happening is the following, or this is at least our proposal. So the solar system actually orbits around the galaxy every 240 million years. And as it does so, it actually bobs up and down through the Milky Way plane. Now, the question of how often that happens is a question of what's in the disk. If there's no dark matter, it would be about a 55 or 60 million year period. But with dark matter, it can match this 30 million year period, and also had the advantage that it could be episodic. That is to say, there's this very thin disk of dark matter, so when it's going through would be when you would get that extra gravitational kick that would knock stuff out of the Oort cloud. So that was our picture. So the solar system's going around the Milky Way, it's bobbing up and down. Every 30 or 35 million years, stuff gets knocked out of the Oort cloud, and that would lead to more likelihood for impacts. And indeed, 66 million years ago, one of these happened. We went through this disk about a couple of million years ago. So if there's basically a 32 million year period, this would match really well. And I just want to say that I don't just talk about this particular extinction, although it is the most recent and also fascinating, because there really is extremely solid evidence that this particular impact was associated with an impact. I mean, when I started my research, I'd heard about the impact hypothesis, but it turns out there's a lot of evidence. You can really look in detail at the geological record and see things, for example, like shock quartz, which is a structural form, a crystalline form, that only happens if there's a nuclear bomb or an impact. And presumably 66 million years ago, there were no nuclear bombs. So it definitely was an impact. And you can also do a measurement of when this happened. And what really made this whole thing really stick together is that they actually found the crater. And finding the crater that corresponded to this impact of 66 million years ago is an amazing story. As I just said, the likelihood of finding it was already, even if you just took into account the fact that 2/3 of the face of the Earth is ocean, was very unlikely. But basically, it was scientists who ended up eventually connecting with geologists at Pemex, a Mexican oil company, who had been doing surveying and had found this circular structure that actually found out what this was. And I tell this whole story, and it's really a great story. So we pretty much know that this happened. And the question is, how do you know what caused things? And I guess my basic point here is that you have to know what to look for. And although right now you probably pretty much knew to look for me, when I was actually on the Big Bang Theory, I was friends with some of the writers, and they just said, why don't you just sit in the lunchroom and just be an extra? And my directing job was to be inconspicuous. And I did such a good job that no one actually knew I was there. And the basic point is that, in science, as with everything else, if you don't say something is there, you usually don't know to look for it. And there's many examples of that, and that's why I think it's really important even to do speculative research, because that's how you find out what's actually going on. And as I said, this book isn't just about this particular theory. It's about really all the remarkable connections that exist between what we see today and what's out there in the universe. I already mentioned that cosmos and galaxies form from dark matter. Cosmological things that form from dark matter collapse. As most of you probably know, that star burning is what produced heavy elements and carbon, such as those that contribute to life. The other thing, though, is that it's actually if you didn't have molecular cooling and actually heavy elements nearby to do detailed molecular cooling, you wouldn't even be able to form structures that are the size of stars, and we would never get our sun. Our planet's geology, hence the carbon cycle in life, rely on the fact that we have plate tectonics, and that relies on nuclear burning in the core of the Earth. So it's sort of like all these little gems that I discovered in the process of doing this. And if our theory is right, it could be that dark matter is connected to the emergence of humans, because after all, large mammals didn't get formed until dinosaurs were eliminated, at least from the face of the Earth. So I think there are all these amazing connections, and they're worth understanding. And a lot of them are crazy, and you wouldn't anticipate them, but are completely solid scientifically. And in the beginning of the book, I try to say 4 lessons that were really important to me and I think resonate throughout. And I think one of them is just how amazing everything is once you understand it, but also the fact that we can understand it. I've talked a lot about the stuff that we don't know, but there's an awful lot that we do know, and it is amazing that we understand as much as we do about the 13.8 billion years of cosmological history that we've had. The other thing that was really important, particularly for understanding the story of how the dinosaurs went extinct, was really combined together many fields of science. I mean, it's really an amazing story that combined together physics and chemistry, geology, paleontology, all of that, and maybe it's even connected to cosmology if what we're saying is true. Another thing that's really important is just how much has changed. I mean, when I gave this book to a friend who commented, wow, it's like learning all the stuff that we didn't know when I went to high school. You know, there's just a lot that we've learned, not just about the cosmos, but about even our solar system in the last 50 years, or so, and it's worth understanding all of that. And I think another lesson that's important when we think about what's going on today is just the rate of change. A lot of things are not new, qualitatively new, but what is different is the rate at which changes are happening, and that's really important to take into account in terms of almost all the things that I discussed. So these were the things that were important to me, and it's all the stuff that part of the reasons that I decided to write a book, but I'll just leave you with this just nice anecdote, which is that while writing the book, I actually went in to give a physics lecture at the University of Bilbao, in the Basque Country, I guess the University of the Basque Country in Bilbao. And my friends know I like the outdoors, so they took me to the beach nearby, and we were walking around, and one of them said, oh, you know, I have a cousin who's a geologist, and do you know the KT layer is nearby? And the KT layer, for those of you who don't know, is basically, it's now known as KPG. It's the boundary layer between before and after the dinosaur extinction, or everything that went extinct. And before then, so you see white limestone separated by a layer of clay. That clay was key to figuring out what had gone on, from a gray layer above when a lot of the stuff had gone extinct. And so that they were no longer leaving these fossils. And it was an amazing experience. So we arranged an outing to go. They'd actually never been. It was really nearby. And if you didn't care about the science, it just was the most beautiful beach in the world. But what's really fascinating about this limestone is that it actually it's used for research and for economic activity, and it's also just millions of years of history are buried in this rock, which is studied to understand in detail how life and geology has evolved on the face of the planet. And, you know, I can tell stories about what we saw there. It's really fascinating. So I don't know if the dark disk idea is right. As I said, it's speculation, but it's something that we will study because the Gaia Satellite will establish whether or not this exists. But I do know, and I think I know a lot more after writing this book, about the amazing connections in the universe and ultimately to life. So if you want to know more about it, you too can. So thank you very much. How are you doing, Ken? So I'm happy to answer some questions. Yes?
Professor Randall, as a result of all this experience you've had, do you come to believe in God or do you not?
What do you think? But you just said about my experience from physics. So I would say, and I actually do talk about this in Knocking on Heaven's Door. I mean, I actually, first of all, I think they're kind of not necessarily connected. I think people like to say it's connected, and I think they're connected only in the sense that we're all trying to answer big questions. But I don't think it leads me to think there's a God. I mean, it's true. I mean, it is interesting, though. I mean, I will tell you that one thing that is interesting is when you kind of look for if you look up sort of what are the sort of miraculous features that allow for life or allow for our planet to have life, such as the stability of the planet, and I talk about some of these, the fact the moon is there keeping the temperature stable. Actually, one of the places you see it is on a religious website because they see all these, coincidences as evidence for that. So some people do like to do it, but my feeling is that I understand things through science to some extent, and that's based on physical processes happening at some particular level. And I really think the role of religion is more sociological or social, and understanding how the universe works, I don't see that it adds to it. Because even any process, even the way we're thinking, we know that at some level it's connected to some physical process happening. Doesn't mean we understand how that happens, but it is ultimately rooted in that. So if you want to believe there's a connection not just to religion but to a God or some higher being, you have to believe that it is actually instructing those atoms in your head to do something at some particular moment, which I personally find unlikely. Yes.
I know your book's about dark matter, but I was wondering if you can enlighten us a little bit about how we know there's so much dark energy. Energy can be detected because of effects on gravity, perhaps, but is dark energy anything like? It's not like the energy we're familiar with. What do we recognize as saying there's dark energy so much?
So really what dark energy is defined by is, we call it dark energy, but again, it's a slightly misleading name. It's really associated with negative pressure. So it's sort of what's known and otherwise as a cosmological constant. So it's stuff that, so one of the amazing properties of dark energy is that as the universe expands, it stays constant, which is a property of negative pressure. Usually we expect it to go down. So it's actually driving the expansion of the universe. And that was the way it was found. It was found through looking at distant supernovae and finding that they're further away from us than we would expect. So the universe had to have been acceleration and had to expand. But the way we know in detail that cosmic pi now is through the measurement of the cosmic microwave background radiation, which basically, we don't just see the uniform radiation in the sky, we see slight deviations from uniformity, known as density perturbations. And detailed studies of those density perturbations corresponds to just how much ordinary matter, how much dark matter there was that sort of was attracting things. And also the fact that it's a pretty flat universe. So putting all that together allows us to establish that cosmic pi. And I'm just going to make one other comment, which you said so much dark energy. And although from the point of view of that pi, it looks like so much, but the real question about dark energy is why isn't there more of it? There's no reason it shouldn't be there, and you would naively have expected there to be a lot more, so much more that pi wouldn't have made sense. Yes. Okay, I'll go somewhere else in a second. You go next. Okay, good.
Dr. Randall, in your book, you talk about a story where you went out to Colorado and you wore night goggles, and you said you were able to see the stars better.
See?
To see
yeah,
the stars.
I was able to see shooting stars at a much faster rate than I would otherwise.
Do you think you could do that here in Philadelphia with the night sky?
Oh, that's a good question. I think you'd still need a pretty clear day. So you'd probably want a day where you could sort of borderline see it. But I would imagine you could probably see more. Like I said, they're not usually used for that purpose, but used for detecting enemy combatants. But you can see things that would be too faint to see with the naked eye. So it's borderline. Okay. Yes.
I read an article that you wrote in the Boston Globe within the last couple of weeks where you talk about the connection between dark matter and race, and you touched on very briefly on something similar.
I talked about
today.
our perception of dark matter, our perception of race, just to be clear.
Right. Okay. So I'm an experimental particle physicist. I'm very interested in making the culture of physics more inclusive, and I worry about the appropriateness of that implied metaphor, and I just was wondering if you could comment on...
Well, so I took out the actual metaphor that you're saying, because it does, for some people, I mean, it's just an unfortunate name that's called dark matter, but that was not what I was saying. What I was saying is exactly the opposite, and in fact, the person where I tell the story, so the story was actually based, I was at an artist retreat known as Yaddo. I was one of the scientists, but I was also writing a book. And so I gave a presentation the day before I left. And in it, I just read from what was then my incipient chapter on dark matter. And I gave analogies to all the stuff that's invisible, that's present. Like I talked about the bacteria in our bodies, where there's 10 times more bacterial cells than ordinary cells. I talked about internet chat rooms. And it was really amazing to me because the day I was leaving, an African-American artist who had just arrived, I hadn't even met him, just stopped me and said, I know this might sound crazy, but were you actually talking about race? So he had actually observed it. And what the amazing thing was that I had actually started talking about race at the beginning, and just all these people that you don't see the same way. And it just came across wrong, but it wasn't meant that way. It was more meant by way of what we're seeing. And I think I've gotten a very positive reaction on the whole, although one person in Twitter did accuse me of being a racist. But that isn't how I intended it. I really intended it saying just the opposite, that there's just lots of aspects of society that you don't see, and how important it is to get outside your own reference frame. So I was talking about in science how we think it's really, we actually recognize the importance of that. I think a lot of people in trying to understand science will sometimes dismiss themselves of responsibility and say, I just don't understand it. But the way you understand a lot of science is by, if you're a particle physicist, looking at life, looking at things on small scales, at tiny scales, scales that we don't see in our daily lives. The way you understand dark matter is by understanding that there can be matter that we don't directly experience. And the way you understand ultra-cultures is by actually getting outside your own reference frame and imagining what it's like to live in another place or surrounded in a different environment. And that's more what I was trying to say.
So I guess the question that I wanted to ask was, what do you see as the responsibility of the physicist or the scientist in society?
I don't think there's any single answer to that. I mean, I think that on the whole, the kind of physics we do gets more and more removed from what people can understand. But as you saw, and as many people saw, people were excited about the discovery of the Higgs boson. And it was really funny when that was happening. I was asked to write a piece for Newsweek, and which I think still existed. And they said we're going to write. We'd like an article on why it changes everything. I said, but actually, it doesn't change everything. Most of the stuff is the same. It just helps us understand how matter, came about or whatever. And she said, well, maybe that's an interesting story. Like, why are people so excited about the discovery of the Higgs? And that is exciting because it was interesting because everyone was excited about the discovery of the Higgs, even though most people didn't understand what the Higgs particle was at the time. They just knew that there was something new that was being discovered. But I think it just showed that there really was a sort of thirst for understanding things that are beyond. I think people like science because it's one of the places we make progress. And understanding the nature of the universe, even if it's not going to help us or have immediate applications, is really important. So I think some people should be explaining it. I don't think everyone is responsible. And I mean, I didn't start doing this until I'd actually established myself and done a lot of important, at least within the community, research. And I think it's important to balance those things. And it's hard to figure out exactly where it is. But I do know that there's enough interest that I think it's worthwhile for some people to be thinking about it. Let me go to the back of the room since they always get neglected. Okay, wristband in the middle of the room. That's you. Person waving your hand. Yep. Okay.
I was wondering, when do you expect that the Gaia Satellite will collect enough data to potentially confirm your hypothesis? And what will you do if it doesn't? Do you have any backup theories?
I liked the way you phrased it. When will it confirm your hypothesis? That was very nice. It's a 5-year mission, so it's collecting data now. And we actually also looked at old data, which isn't as accurate in Hipparchus data. So, within a few years, we should really have a much better idea of what's going on. And if it doesn't, I mean, people have this vision that, we're so fixed on our theories. I mean, I know that, not just my theory, but mind you, most models that people come up with are wrong in the sense that most of them are not going to be verified. There are ways of understanding what is true and what isn't true. So it's not that we get tied to one, but you try to figure out what all the consequences can be. How will you know about it? What it would connect? But it's not the only thing I will be working on during that time. And I'm working on other models of dark matter as well. So I will happily go on and be glad we know a lot more. But, of course, it would be really nice if they discover it. Yes?
Mistake. Hi. I appreciate your lecture. As you probably know, Dr. Vera Rubin's from Philadelphia, and my question is, and I'm sure you have no direct impact on this, is I'm like a one-man quest to get her Nobel Prize for physics. Other people, for instance, for dark energy, for finding that the neutrino has mass. Even two guys, I can't make this up, with a roll of Scotch tape and a block of graphite won the Nobel Prize for physics. So my question is, the only thing I can think of, because other things been awarded, is that she's a woman, and that's detracting from the situation.
Well, I don't know, but I mean, check Twitter. I mean, they had this list of people that should win the Nobel Prize, and I was like, why isn't she won a Nobel Prize? I totally agree with you. I think it's really strange. And the arguments that are given are really strange, like we don't really know what dark matter is, and you could say the same thing about dark energy, so I completely agree with you. I do not understand why she didn't win a Nobel Prize. Don't. Yes?
I'm not a physicist, systems neuroscience actually, but my question is really about your first or second slide that you showed was the inflation. So if the universe was, the accepted theory is that the universe began with a specific set laws and that there's a specific set amount of energy, dark and non-dark and so forth. So how much of the universe is deterministic?
So first of all, I said very clearly we don't know how the universe began. So I don't know what it began with. I do know that later on in its evolution, it had all these different things at present. But I don't know when they get formed. I don't know if there are other universes. But I try to focus on the things that we can actually measure and study, which is what we have after the Big Bang, when all of this is happening. And so you can ask those questions. Those are philosophy questions, and they may or may not have an answer. But there had to be something there in order for all of this to make sense. In this universe? How much of the formation of our universe
is deterministic?
So a lot of it's deterministic on a statistical basis. So we know things like the density fluctuations. We know what kind of structures that would form. We know what kind of shapes of galaxies. And we think it's deterministic to the extent that when things don't agree, we think it's telling us things about the properties of dark matter, for example, which is one of the things that's being studied today. I said things way too many times in that answer. Okay. In the back of the room, all the way in the back.
Professor Randall, would you mind commenting on the current political environment for science and whether it is, particularly in whether you believe it's mostly rhetoric or what kind of impact that might have on scientific research?
Well, it's funny because I think that we hear a lot of anti-science stuff. I think there's a lot of people who support science. I mean, I think for me, what I see as understated is that we support a lot of sort of what I would call applied research. I mean, some of it is described as basic research, such as medical research, but a lot of it, there's sort of a directionality to it. And the example I like to use is, although we're doing a lot of research on, for example, genetic origin of diseases, I mean, the fact is that DNA research was basic research. When we discovered DNA, that was basic research. No one was thinking about solving cancer at that time. And I think it's really important that we support basic research more. And I think a lot of our science support, and there is still a fair bit of science support, I think it's more directed. And I think, obviously not all basic research is going to pan out, but I think the big discoveries, it's really important to allow those to happen too. And I think there's less and less support for that. Over there? Back of that column. Oh, I was actually pointing to the woman over there, but you can call on him too. You can call on both of these people. Both of these people came here. I just want.
Hi. So thanks for the nice lecture. I was actually, I read your Boston Globe article as well, and I was a little sad by it too. So unlike the bacteria you can't see in your body, the other people that's not of your race have feelings. And so when you make that sort of comparison about understanding something that you can't see at first and learning empathy and things like that, I think there's that assumes that everything is equal and there's forces that are equal and opposite, just like physics. And a lot of times I think if you want to talk about society and race, that's not true. And so in the context of physics, I think it makes sense. But I also thought...
So again, it's not about any underlying assumption of equality. It's just saying that it's important to look. That's all I'm saying. That you just have to see things from different perspectives, get outside your own perspective. And that's the only way you make progress in understanding making connections outside the ones that you would make just by what you see every day in your life. And so it's just advocating getting outside your reference frame. It's not advocating making any further assumptions. And actually in science, it's also not true that everything is equal. Some things are a lot more interesting than others. It's just that you don't find them until you actually look, and then you can figure it out. And so the person who accidentally got called on, we should let them talk. Okay.
Hi, Dr. Randall. I really enjoyed your talk. I just had a quick question. You mentioned that there could be a portion of the dark matter that interacts with this dark light, which is part of your theory. Is there any way to know that it couldn't be all of it or a greater amount, or do we have any sort of sense on the scale?
Well, so what was critical to our theory was that it would be able to radiate and form a dark disk. And there is a lot of evidence that there is this sort of spherical halo. So if all the dark matter did that, that would be ruled out. And if the interaction was too strong, things like the bullet cluster wouldn't work, which shows that most of the dark matter isn't interacting a whole lot with itself. So there is evidence that not all the dark matter has strong interactions. Most of the dark matter can have some weak interactions, or some of it can have strong interactions, but it can't be both. Okay, apparently one more question. I'll let you choose the person, then I don't want to be responsible. Okay.
The question I have is, if dark matter does not interact with light, if this question is even relevant, does it, the association between energy and mass in terms of Einstein's equals mc squared equation, does that apply, or do we know?
Yeah, so Einstein's equation has nothing to do with these other forces, which are, so it's just about, it's actually how things interact with gravity. And actually, it's a little more complicated because it actually involves momentum too in the full formulation. And yes, that would still be true of things. So, and that's one of the things that we want to be clear on, that it's just a property of the matter that's there. It's whether it has charge or not. So yes, it would still be true. So you've been a great audience. Thank you very much.